Okay, we're on the last section, 6-7. I want to turn to that. Page 342. Most of the time when you have to analyze something in the context of a real situation, you spend some time measuring, like in a lab. You count how many flies are born or grow each day, and that's a really tough job, counting flies. But they do that. Yeah. I have an example in my calculus text that's about Drosophila flies, and you start out with a pair, a mating pair, and they have a bunch of offspring. Every day you've got to count and see how much they grew. How do you count flies? How do you keep track of them flying around? How do you count them? Any idea?
Fish scanner. You color them.
You color them. How do you do that without killing them? The Drosophila flies are the little fruit flies that bug you when you open up the little dudes. You know, how do you count them? It's really cool how they do it. They get a thing that's called a photo gate. You ever heard of a photo gate? When something passes a photo gate, it breaks a line of light, and then by breaking that triggers up something, either a counter or a timer. Sometimes the timer will start until that laser light is broken again. That way you get really, really accurate data. If you can get something to go through this one, and it's connected to another one down here, and it goes through that one, it'll tell you exactly how much time it took to the nearest 6 places. It's amazing. You can also do it with little teeny tiny Drosophila flies, although it takes a tremendous amount of preparation and design, because what you do is you have this case of Drosophilas, and you've got this little teeny tiny laser thing without only one fly can fit through at a time, and then you give something enticing to them over here. And they will fly through one at a time to go get that food. And they'll count for you. Then you put it backwards the next day, and they fly from here to here. Keep them starving, but alive. And they'll do that, and it goes pretty quick. It's amazing what people can do when they're motivated. Anyway, so what they do is they gather data, like flies on a day. On this day there were 14. On this day there were 24. On this day there was 57. Whatever. And then they gather that data, they put it in the table. And then what you have to do is analyze the table as mathematicians. That's what we're doing. We analyze the data that's been collected and try to decide what sort of a function fits through it. Is it a line? Is it a linear relationship? Will a quadratic fit it best? Depends on the situation, it depends on your data, or maybe it's exponential, or maybe it's logarithmic. Knowing a little bit about those curves and knowing a little bit about how the numbers behave can help you decide what sort of a function fits the data when you analyze the numbers. That's what we're doing here. That's what we're doing in this section. Okay? So look at example 1, please. Page 342, example 1 has an A and a B set of data. And this is what we are to do. Determine the type of function represented by each table. The first thing you have to do on any of this sort of data analysis before you can make a decision is to make sure that the x values are incremented evenly. And look, in the A part we have -2, -1, 0, 1, 2, 3, 4. They are incremented evenly. They don't have to be incremented by ones. They just have to have the same space in between. So the B part is -2, 0, 2, 4, 6, 8, 10. Again, incremented evenly. If they weren't, you couldn't do what we're about to do. But you should check in case it's real live data. Then if they're not incremented evenly, then you got to go to something else. You got to figure out something other way to analyze it. But since they are, now we're going to focus on the y values. I want you to look at the solution on page 342 and look what they do with the A part. The first thing the author checks, the first thing you should check, is to see if each of the y values is a common multiple of the one before. And it's weird because the way you actually analyze it is by division. Notice what they have in the solution part down there in the red for the y's. They say if you take 0.5 times 2, you get 1. If you take 1 times 2, you get 2. If you take 2 times 4, you get 2. If you take 4 times, 4. If you take 4 times 2, you get 8. So forth. So whatever you get, if you multiply it by 2, you get the next y value. That's, and you're going, well, that's going to be kind of hard to tell if I get the same thing every time. Here's a better way to analyze and realize that that's a 2 every time. Go backwards. What is 16 divided by 8, for example? We go backwards. 16 divided by 8 is? What's 8 divided by, what's 8 divided by 4?
2.
What's 4 divided by 2?
2.
That way, if you go backwards, you can do some division and not only figure out if it's multiplied by the same thing, but what that thing is. It's 2. You understand what I'm saying to you? If you can't see it in the forward direction, then take any element and divide by the one before it. Then take that one and divide by the one before it. If you keep getting the same number, then you're talking about an exponential equation. Because if you'll remember this at the very beginning of the chapter, this was what we used for an exponential equation. And this thingy, if you'll remember what that was, that's the thing that keeps getting used over and over again as a multiplier this many times. Guess what this is in this situation? 2. That's what gets used over and over and over again to get the next successive y value. That's why it's exponential, because you've got something, this thingy, being used again and again and again as a multiplier. That's what this means, b times b times b times b times b. And it's 2 in this case. What would be a in this case?
Would it be
The beginning amount, which is 0.5. So we know this. It's going to be 0.5 times 2 raised to the x. Voila, exponential. Not only that, we know what the exponential function is. We determined it was exponential because we multiplied by the exact same number every time. That's what this guy is. If this is 4, then we're going to multiply by b 4 times. Well, b happens to be 2. Do you see how this all ties together? Okay. Now, take a look at the b set of data. If you look at the y's on that, go down a little bit on your solution. Take a look at those. If we want to decide if this is exponential, that should be your first thing that you decide. Is it exponential or not? You would take, for example, I would take some small numbers, but I would go 18 minus 8. You see where I'm at? Not minus. 18 times 8. Try that again. 18 divided by 8. That's not something whole. However, 8 divided by 2 is, which tells me I'm not getting the same thing when I take 18 divided by 8 and 8 divided by 2 and 2 divided by 0. 2 divided by 0, that's horrible. Can't do 2 divided by 0. But can you see that 50 divided by 32 and 32 divided by 18 and 18 divided by 8 and 8 divided by 2 are not the same number?
Yes.
So it's not exponential. You following me? So now we got to go to something else. And you learned this in a previous section. Next thing we would try, if it's not a common divisor or a common multiplier, how would we do that? If that doesn't happen, then you start checking out common differences. And so we take, for example, not divided by, but minus. 50 minus 32, that gives you the 18 on the end, the blue 18, you see it? 32 minus 18 is 14. 18 minus 8 is 10, so we're doing subtraction now. And we do not get the same number in the blue row. So we try it again. 18 minus 14, that's 4. 10 minus 6 is 4. 14 minus 10 is 4, skip that one. 6 minus 2 is 4, 2 minus negative 2 is 4. It took 2 sets of differences to get the same number every time. Guess what fits this best? Quadratic. A quadratic, because 2 is the thing on x, the exponent on x that defines or that identifies a quadratic, and it took 2 differences. 2 sets of differences to arrive at the same number. Tells you a quadratic will fit this data best. And a quadratic looks like this, if you'll remember. That's the vertex form of it. Do you remember? Or you're going to look at it like this. This is the general form, or the standard form. Or whatever. This one's a little harder to make the data fit, but you can put this data in your calculator and do a quadratic fit. And tell you the equation. You know what I mean? You done a quadratic fit before? Remember, you put the x's in list 1, the y's in list 2. Build the window big enough. Turn the plot on so you can see them. Go back to stat. Over to calc, down to quad reg. Why quad? Because it took 2 differences to get the same number. So you go to a quad reg. List 1, list 2, y1. Enter. And it will fit a quadratic curve. And that quadratic curve will be in the y equals screen. Do I have to go over that with you again? Anybody? You do? You want to see that again? I will do that for you in a few minutes. I don't want to get that whole thing out again and rig this thing up. I want to finish the lecture, and then I will come back and show you how to fit it. But you understand why we determine a quadratic fits it best. 2 sets of differences. And 2 is the defining factor for an exponent on a quadratic, right? You see that? Okay. Now look at example 2. I'll come back and show you how to do a quad fit if you decide that's what fits. All right. Example 2 says, now it says write an exponential function of the form y equals ab to the x. This shouldn't be that scary. We already did that. It wasn't that hard when we decided an exponential fitted us. Oh, this is rough, because it's not a set of data. Notice there's no table in example 2. Oh, brother, this one's gonna take a little more effort. I wanna watch this. It says, write an exponential function of the form y equals ab to the x, because that's our standard, whose graph passes through 1, 6, and 354. We only get 2 points. So this is our standard here, but it's gotta go through, I'm gonna put it out here, 1, 6, and 254. Is that right? 254? 354. I can't even plot it on there because 54 is a y value and I can't even count up 54. First of all, there's not enough spaces and I'm not even close to tall enough. So I can't graph that for you, but I can give you kind of an inkling of what's going on. 1, 6 might be located about right there. That would mean that not 1, 6. That would be 0, 6. 1, 6, if I incremented these by 1s, but I incremented these by 10s, 10, 20, 30, 40, 54. Okay, so 10, 20, and so forth. This is 1, 2, 3. 1, 6 would be about right there, and 354 would be about up here. So we want an exponential that has that kind of shape that contains those 2 points. Do you understand what we're after, at least? We got to come up with the equation for this. That's going to be kind of rough. We don't have a beginning amount because the beginning amount will be where it hits the y-axis, and we don't know what that is, so we can't put an a in there. Here's what we can do. Watch carefully because this is an involved process. We can use this equation and this point and write as much as possible, which would be 6 equals a b to the 1. Do you understand that? I can do the same thing with this one, and I would have 54 equals a b to the 3. And whether you remember this or not, if you have 2 equations with 2 unknowns, and you're clever, you can find those using the 2 equations with each other. What you got to do is use one of them, probably the one with the smaller exponent. You need to use one of them to solve for either a or b, and then substitute that value over here so that you have an equation that has only one variable in it. That's the whole notion of substitution. We're used to doing substitution this way. Just to remind you, if you have 2x plus 3y equals 7 and y equals 4x plus 2, substitution, the whole nature of it, this is your 2 equations with 2 unknowns. Substitution means, oh, good, I got y equals something, so I'm going to replace a y with that. Then when I write the equation replacing y with this, I'll have an equation that only has x's in it, which I can solve. You see what I'm saying? Same thing up here, only these are exponential functions. It gets kind of rough, can be. Since that's a 1, I don't need to write it. So what I could do is I could solve for b, say for example, 6 over a equals b, and then use that value of b over here. Do you see the substitution happening? And so you would get 54 equals a times 6 over a to the 3rd. That's one way to do it. Let's see what happens when we do this. You would get 54 equals, and this will be 216 a times 216 over a cubed, because I'm using the cube on both pieces of the fraction. You follow? Everybody clear? Okay. And this a is understood to be over 1, which means that this a can cancel with one of these. Did you catch that? See what's going on? This a out here cancels with one of these 3 a's down here, and I have 2 left. Yes?
Why would it cancel like really multiply?
No, this is a over 1.
Oh.
Like that.
And then
And a is on the top here as a factor. It's on the bottom. It was cubed here as a factor, so I'm going to lose one of these and one of these. You understand? Okay. So now what I have is, I'm going to erase this because it's nothing to do with the problem. I'm going to come up here so you can still see. I have 54 is equal to 216 over a squared. That's what I have left because that a canceled. Are y'all following so far? Okay. Then we got to remember this. Whenever you have a fraction equal to a fraction, cross multiplying is a good thing to do. And you're going, but I don't have a fraction. Yes, you do have a fraction equal to a fraction because any number could be placed over 1. 54 is over 1. I'm not going to do that for you because you're sophisticated enough. You don't need that. This is a numerator times the denominator equals 1 times 216. That, the cross multiplying. Then we divide by 54. What's 216 divided by 54? 4? Is it 4?
Yeah.
Then A is 2. We got one of them now. Since A is 2, and that took an awful lot of work. That's a lot of math right there. Since A is 2, what is B? What is B? 3. Come back over here where we had B isolated. You take 6 divided by what we got for A, and that's 3. So we come back over here, make another substitution, and 6 divided by 2 is 3. Now we have enough to write the equation. We know what A and B are. So the final answer is, I don't know where I'm going to put it, I guess right up here. Y equals A, B to the x. That function will have this point and this point on it. And this is the answer to the question. That you have to go about solving a system of equations to find A and B. You want to do it again? Actually, I'm going to do exactly the same problem again, only this time, when I do this one right here, I'm going to solve it for A instead. And we'll see what happens. You can decide which kind you like best. Okay? But I'm going to erase this because I got to stay on camera. Yeah, it's all still visible there. Okay. So I'm going to start out with the same situation here. Using this as my standard. I haven't come up with this yet. We'll pretend I haven't. And we're going to do this problem using that as the standard, and I'm going to write this thing again. I'm going to write 6 equals A, B to the 1, and 54 equals A, B to the 3. I'm going to start out the same way. But when I go to solve this one with the smaller exponent, this time I'm going to solve it for B. So it's going to be 6 over A equals B. Did you follow that? That means I'm going to take this value of B and substitute it in over here. Did I just do this before?
Yeah.
Oh, try that again. Sorry about that. Let's do that again. What do I want to solve for?
A.
You want to get A by itself?
Yeah.
So A, well, I might not be able to see it if I flip it around. 6 over B is A, right? So I'm going to substitute this in for A. And I get this equation. 54 equals 6 over B times B cubed. Remember, that's a numerator. So that's why I'm putting it up there, because that's understood to be over 1. And so I've got a B down here and 3 B's up here. That gives me 54 equals 6B squared. Did you follow that in the canceling? This cancels one of these B's, leaving me with 2 of them. So I've got 6B squared on the right. We good? 6 goes into 54 9 times. And so B is 3. That was a little quicker. But you can do it either way. What we have now is what B is. We got to figure out what A is. What's A going to be? 2. That's what we got before. When you come back here and you say A equals 6 over B, and we know that B is 3, then 2 is A. We have both of these things, and we write the equation. Y equals A, B to the x. We get the very same thing, but notice how much quicker this one was. The other one had to go clear over here and come down, but you can do it either way if you follow what's going on. If you like this one better, then try to remember, you want to isolate A first. You want to get A by itself. And then substitute that first value with something with a B in it. It usually goes faster that way, but it could be done either way. We okay? Can we move on? So when you've got 2 points, you've got 2 equations, and they have to work simultaneously together by substitution to get the values of A and B. Okay, I'm not going to do example 3 or 4. We're going to clear over to 5 on page 345. Okay, example 5 says, use a graphing calculator to find an exponential model for the data in example 3. Oh, we didn't do example 3. That's okay. We're going to still use the data from it to do example 5. They didn't want to print it again. Use the data in example 3. Then use this model and the models in example 3 and 4 to predict the number of trampolines sold in the 8th year. What? Looks like we're going to have to read example 3 and 4 anyway, just to get an idea of the context. We're not going to do those particular examples. So go back. Let's read again. Example 3 says, a store sells trampolines. The table shows the numbers Y trampolines sold during the X year that the store has been open. Write a function that models the data. So in the first year they were open, they sold 12 trampolines. In the second year, they sold 16. People, the word's getting out. This is the place to buy a trampoline, apparently. Okay? They keep selling more and more and more trampolines as we go along. Now, you could take the Y values and analyze them the way we did in example 1 and see what's happening, if you wanted to. I prefer to dodge that step and just look at what I've got going there in a graph. So hang on just a minute. Let's look at example 4 because they're going to make us use that too. It says use the data from example 3. Create a scatter plot of the data pairs x, y. No, we're not doing example 4. We're not touching example 4. We're going to use the data in example 3 and come up with an equation to answer example 5. Okay, here we go. Wasn't going to get this out yet, but I guess we need it. Now, Court, you said you wanted to show me how to fit a quadratic. I'm going to fit an exponential to this, but when you fit a quadratic, as I get there, I'll show you how to handle that one too. That way we get 2 kills with 1. Kill 2 with 1.
So if we go, it's that.
Alright, should have left this out, I guess. Alright, I gotta move my viewing student. Hang on a minute. Sorry, this is gonna be rather dizzying for a moment. If you view that video, you may want to look away as that was going round and round. Can you all still see? Got to get it a little bit closer to the TV. Okay, can you all still see right here? Yeah, okay. All right. So take the data from example 3. Do this on your calculator. Do it with me so that you punch the buttons at the same time. From example 3 in list 1, so we go to stat, edit, dump any list that you've got. I've got a lot. That's it. Okay, and just put 1 through 7 in. And then for the trampolines, 12. You better all have a calculator in your hand. If you don't have one, I better loan you one because you need to punch these buttons in order to make a memory to have to do this. You got a calculator, Court? Oh, I didn't see that. Didn't see it. Everybody got the data in and remember how to do it?
Yeah.
What do we do next? No. Build a window. The x's, which was 1 through 7, we should let go from maybe 0 to 10. The y's go from 12 to 96, so I'm going to go from 0 to about 120. A little bit on the front, a little bit on the back. By tens is fine. Do you understand why I built the window the way I did? You don't. This isn't necessarily correct, but do you understand my choices of numbers? Then what do? You go to y equals and erase anything that doesn't have to do with this problem and turn plot 1 on. You remember? Now, with our experience on this, that graph could be, it could be exponential or it could be quadratic, right? In example 5, it says fit an exponential. It tells you what to fit. If you're trying to make the decision which one fits better, this is how you decide. They told us it had to be exponential. So we have no choice. Even if we decide a quadratic fits it better, we have no choice. It says exponential. But if you're trying to make the decision, here's how you do it. You go back to stat, over to calc, and I think a quadratic fits it best. We'll pretend that's what I think. So I'm going to go down to quadratic, quadrag, y'all there? And you have a list 1 and a list 2. I've got list 3 in there because that was a different problem. So I'm going to go second and the number 2 to put a list 2 there. So it should say list 1 and list 2. And then down here on store, I'm going to put that y1, so it's vars, y vars function, y1, and then calculate. Do all of you have this R squared value?
Yeah.
That's a darn good fit, 0.996. I'm waiting for somebody to catch up, hang on.
This is the word.
Has everybody got the R squared diagnostics on? And do you see that a quadratic is a really great fit? See it? Okay, now, remember that. 0.997 basically is what that is. Remember that. Now go back to stat. Oh, wait till these guys catch up. Are you caught up or what?
Yep.
Okay. Court, you caught up? I guess you were never behind. It was the guy in front of you. What's your name? James. I'm sorry. I'm learning these very slowly. I'm sorry. Okay. Anyway, so we got a really good fit, 0.997. Now go back to stat, over to calc, and clear down to exponential regression. Because that's what they told us to fit it to, right? Well, I want to see how good a fit that is. Let's do an exponential rate regression. Hit enter. List 1, list 2. Store it in Y1, bars, Y bars, function, Y1, and calculate. This one has an ever so slightly better fit.
0.98.
Only slightly better, but still better. And so if you were trying to make the choice which one to fit it to, you would choose the one with a better fit. And this is only slightly better. So I'm going to keep this one because that's what they told me to do in the first place. But if I had to make the decision, that's how I would make it. So go to page 345 and follow the instructions. It says use the graphing exponential model, which is what we've got here, from example 3. Then use the model and the model from models in example 3 and 4. We're going to dodge that one. To figure out how many would be sold in the 8th year. How do you use that? How do you find out how many would be sold in the 8th year? How do you predict that based on your graph?
You go to 8 and find value.
Well, first you go to the graph, right? You got to look at this thing and see, and it's a pretty darn good fit. It takes a little while to do an exponential. It was a pretty good fit. And then we use this graph to predict how many trampolines they'll sell in the 8th year. How do you do that? You go second and trace, second and calc. Remember the trace key with the calc above it? A value at 8. Enter. They are predicted to sell about 139 trampolines next year if this continues, this trend. Now that can't continue indefinitely because it won't be long before they're selling hundreds of thousands. It cannot continue, but what? In the words of the problem, it said, predict the number of trampolines sold in year 8. You following me? But you don't write 138.8 because trampolines come in whole trampolines. So we would write 139. You understand what I'm saying? Does everybody remember how to make your calculator work for you here all the way to the end? Your exponential regression is actually found below the screen, so you got to keep going down, down, down until you see EXPREG. Last thing, and I think I've got time for this, but we're not going to have any time to work. Last thing is example 6, new set of data. Let's see if we can apply everything we've talked about. Take a look here. It says the atmospheric pressure decreases with increasing altitude. Are you aware of that? The higher up you go, the less air there is to breathe. Fewer oxygen molecules because the air is thinner. There are fewer particles making it up. At sea level, the average air pressure is 1 atmosphere. The table shows the pressure P, that's atmospheres, in atmospheres. It's a strange unit, but that's what we call it. Shows the pressure P in atmospheres at selected altitudes H. So H stands for height up above the ground, above sea level, and P stands for the pressure there, pressure of air. Use a graphing calculator to find a logarithmic model. So they're telling you what model. That's great. Of the form h plus a plus, let's see, h equals a plus b log p, natural log. Notice they've got natural log. Thank goodness that's what your calculator has too, is a natural log regression. That represents the data, and then estimate the altitude when the pressure is 0.75. So same process. Start over. Where do we begin? Stat. Edit. Dump those lists having to do with trampolines. Remember how to dump a list? I hope. Now, take the data from example 6. If you get lost, let me know. Remember how to dump a list? You go up to the list itself and you go clear enter. Okay, so now take the air pressure and the altitude stuff. Put that in there.
Jay,
What?
my calculator is kind of being weird. It doesn't have like a. It doesn't have anything less than like a 4 on it.
On the list?
Yeah.
It's because you deleted it, you bum.
Oh. Whoops. Let me see.
Probably instead of clearing them, you deleted the entire list.
Oh. Shoot.
I will fix yours in a minute. Let me get through this and I'll come and fix it.
Oh, I just fixed
I
it.
can show you.
I just fixed it.
All right. Let me finish this and I'll fix any calculators that have problems. But this is where you put your list 1 and list 2. Do y'all agree? Everybody clear? All right. Now it's said to do a logarithmic one. Well, wait. Let's go to the window. This is a pretty tiny window now. Let's go to the window. And notice that our x values range from 1 to almost 0. So I'm going to let the y minimum be negative 0.5. I'm sorry, the x minimum and the x maximum be 1.5. That's all the bigger the range is. The y's go from 0 to 25. So I'm going to go from negative 5 to, I don't know, 30, 40. I'm going to go to 40. Oops, did that bad. Negative 5, 40 by 10s. Okay? That's those are my decisions. And then I'm going to go, after we built the window, we're going to do what? Not yet. Go to y equals and clear out anything that doesn't have to do with this. This was about the trampolines, so I'm going to get rid of that. So I'm looking at only my plot. That doesn't look like a logarithm. Yes, it does. It looks like a logarithm that's been reflected twice. It's still a logarithm. Okay? So, here we go. We're going to go to Stat, over to Calc, and way down till you see ln reg. This is a linear reg, not a log. This is a log reg. This is a natural log regression. See it? Y'all with me? That's what we're choosing. Enter. List 1, list 2, y1. So we go vars, y vars function, choose y1, and calculate.
That's pretty good.
That's a nice fit.
The R. That's what you look at.
Notice this tells you that this is the kind of equation they're using, which is a plus b log x. Do you remember in the statement of the problem it says write it in the form h equals a plus b log p? Well, h is y, it's our height, and x is our pressure. So this is of the right form. Okay, graph it, see if it fits. Nice, it does. Nice fit. And then it says, estimate the altitude when the pressure is 0.75. What do? You go to Calc, his second trace key, Calc, a value at 0.75, because 0.75 is an x value. 2.71 what? What are the units?
Okay.
Is it kilometers?
Where do we get kilometers from? Oh, it says h is in kilometers, yeah. So this would be 2.7 kilometers up. Any idea how many miles that is? Is it more than 1? Is it less than 1?
It's like a little.
It's a little closer to 2 than 1, but it's between 1 and 2 miles. 1.6 kilometers is a mile. Okay, y'all see what you're gonna do? This is really an exercise in regressing different types of models. Happens the same way as it does a linear regression. And I'm just about out of time and I'm out of material, so that's good. Okay, so sometimes you're gonna have to decide if there's a common ratio, in which case it's an exponential model, or sometimes you're gonna have to take differences until they're all the same, which tells you it's a polynomial model of some kind, quadratic usually. Or if it tells you what kind of curve to fit to it, you gotta find that in your calc key, in your stat. All right, this is the assignment. There's only 13 questions. It's not a big deal. 6.7 is 3 through 23 odd and 33. Good luck. Happy weekend.
My calculator is not working.
Oh, no. Okay, I'll come fix this as I turn this off. See you, bye.
Is yours still glitching?
Mine is glitching. I can't turn it on.